Hey everybody, welcome back to another vector statics worked problem video. In this video, we're going to be solving a rigid body equilibrium problem in 3 dimensions. Okay, so this is the setup of the problem here. There's a blue beam that's protruding out from point A, and it's suspended in place by these 3 yellow cables. There's also an applied 300-pound force in the minus J direction at point C, and we're asked to figure out how much tension is in each one of these supporting cables. We're also given that at point A, the way that the beam is supported is by a ball and socket joint. And critically, there's this other piece of information that states that at point B, there's a frictionless pulley. Now, the way to think about this is basically that from point E to point B to point F, that can be considered as one continuous cable, and it's just fed through like a frictionless eyelet at point B. Now, it's a pretty subtle point, but it actually has to be this way because otherwise this problem would not be solvable. The reason being is that if cable EB and cable BF were 2 totally separate cables, just happened to be attached at point B, well then there would be no coupling between the XZ horizontal plane and the vertical XY plane, meaning that there would be no connection between the 300-pound force in the vertical plane and the tension in EB, which is also in the vertical plane. There'd be no connection between those forces and tension in cable CD and tension in cable BF, which are both in the horizontal plane. In order for this problem to be solvable, they give us this hint that there's a frictionless pulley at point B, and that's the link between the vertical and the horizontal planes here, because the cable tension in EB is the same as that in BF, because we can treat that as one continuous cable. So anyways, as with all rigid body equilibrium problems, the first thing we want to do is to draw our free body diagram. So in our case here, there's 4 very obvious ones. There's the 300-pound force downward at point C. There's tension in cable CD, and then there's tension in cable BE, as well as tension in cable BF. And again, because of our assumption that there's a frictionless pulley at point B, we can assume that TBE is equal in magnitude to TBF. And so for the remainder of the problem, we're just going to refer to the tension in both of these cables as T. In addition to these 4 obvious forces, there's also a reaction force at point A. And because this is a ball and socket joint at point A, that basically means that the end of the rod at point A is constrained from moving in the X, Y, or Z direction, but there's no limitation on how it can rotate about that point. So the way that we express it is basically 3 forces, RAY, RAX, and RAZ. We've got to include all 3 of those components of the reaction at point A because they're all independent forces. So as far as just counting up the number of unknowns here, we've got 3 at point A, we've got a 4th one here, TCD, 5 and 6 if we consider TBE and TBF separately, but they're actually the same. So 5 unknown quantities in this particular problem here. Now when we're doing problems in 3 dimensions, the number of equations that we have actually jumps up from 2 dimensions, where we only had 3 equations, to 6 equations in 3 dimensions. We've got sum of forces in the X, Y, and Z direction, that's 3, but also the moment equation. So if we take sum of moments about any point, that actually contains 3 independent equations because we're basically summing moments about each of the 3 independent coordinate axes. So in our case here, we're actually only asked to find the tension in each one of the cables. We don't actually need to find the reaction at point A for this problem. Now that actually lends itself to taking moments about point A, because if we take the sum of moments about point A, then none of these 3 reaction components at point A are going to contribute a moment about that point. And the reason there is because the lines of action of all 3 of those reaction components, they all pass through point A, so they're not going to impart a moment about point A. So the strategy here for solving this problem is we're going to take the sum of moments about point A and set all those equal to 0. Now we should think for a moment about how many terms are going to be in this equation. Again, none of the 3 reaction components, RAX, RAY, and RAZ, are going to be a part of this moment equation, but there are 4 additional forces, the 300-pound force at point C, TCD, as well as TBE and TBF. All 4 of those forces will contribute to a moment about point A. So my strategy for these more involved problems is to always start with a symbolic roadmap to solve the problem. Now what I mean by that is let's just set up the equation that we ultimately need to solve, and then we'll plug in the specific numbers a little bit later on. The sum of moments about point A, well again, there's going to be 4 of those. For this force T sub BE, the moment of TBE about point A, well, that's going to be R from A to B cross TBE. So the moment arm is always equal to the vector starting at the point about which we're taking moments, which is point A, and going to the point where the force is applied. So that's why R in this case is RAB, and then we're crossing that with T sub BE. So that's going to be the moment due to the force TBE. There's another moment due to TBF, right? So the moment of TBF about point A, well, that's got the same moment arm because both those forces are applied at the same point. So again, we have R from A to B. This time we're going to cross that with TBF, right? So that's a separate moment. It's a totally different moment, and it's due to this other force TBF. There's another moment due to this tension force TCD, right? So you can imagine if you pull along cable CD, that's going to tend to want to rotate this blue bar about point A, and that's the moment that we're trying to figure out here. So the moment arm corresponding to TCD is going to be the vector from A, not to B, but all the way to C. So we're going to have RAC, that's the moment arm for this moment here. We're going to cross that with TCD, right? So that's the moment of TCD about point A. And then lastly, there's actually a fourth moment. There's an applied force of 300 pounds at point C as well. Again, the moment arm in this case is again RAC because these forces are applied at the same point. But this time we're not crossing with TCD, we're crossing with the known force of minus 300 pounds in the J direction. Right? So that's the sum of all of the moments about point A, and all of these should sum to 0. Now we move into the next part of the problem where we just have to populate and figure out what all these vectors are. Okay, so this part is going to take a while, but I think this is the most organized way to approach one of these problems. You're just going to basically tabulate what all these vectors are. So let's just start with RAB. That's the vector that goes from point A to point B, and we just need to express that as a vector. So to figure that out, you just imagine that you're standing at point A and you have to figure out how to get to point B. Now in this case it's pretty straightforward because it's all along the x-axis. So to get from point A to point B, we just have to go 3 feet in the I direction. That's the whole vector because there's no y or z component. And if you notice, RAB actually shows up a couple of places. It shows up here and here. So we've actually knocked out 2 of the vectors. All right, so next let's tackle RAC. Should be no surprise here, but RAC is also along the x-axis. It's just to get from point A to point C, we have to go 3 plus 4 or 7 feet in the I direction. Nothing too tricky about this. RAB, RAC are both along the x-axis, so that knocks out 2 additional vectors for us. All that's left is to figure out these 3 vectors, which is going to take a little bit of time because these vectors are not along any of the coordinate axes. Okay, so let's start with TBE. So this is a force vector, and it's the force that goes along the line from point B to point E. It's the tension in this cable from B to E. Now, how do we describe that force as a vector? Anytime you have this situation where you need to define an arbitrary vector in 3-dimensional space, the unit vector approach is really helpful. Okay, so what I mean by that is the vector TBE, well, that's equal to some magnitude, we're going to call it TBE, times some direction. We'll call that lambda BE, right? A vector is always equal to a magnitude times a direction. That's kind of what we always learn when we're first learning vectors. This TBE here without the overbar, that represents the magnitude or essentially the length of that vector. And this lambda here represents the direction that is pointing in 3-dimensional space. We've got a strategy for figuring out these lambda vectors. Okay, so lambda, this is just a dimensionless pointer that points in the direction from point B to point E. And the way to figure out lambda is to go back to the given geometry of the problem. So lambdas are always going to have the same form. If we're trying to calculate lambda sub BE, the formula is figure out the vector from B to E, and then just normalize that by dividing by the magnitude of that vector, right? So if this was lambda AC, the equation would be the vector AC divided by magnitude AC, and so on. Well, in order to do this, now we go back to the geometry here. What is the vector from B to E? What you have to ask yourself is, if you were standing at point B, how would you get to point E? That's really the question that we're trying to figure out here. And so you can see that you'd have to travel in the x direction, -3 feet. That would bring you back to point A. And then you'd have to go up an additional 3 feet to get to point E. So the way to describe the vector BE would be -3 in the I direction plus 3 in the J direction. And of course, it's going to have units of feet. Right? That's the vector that goes from point B to point E. So -3 in the x direction, plus 3 in the I direction. Now, this here is a vector, right? -3i plus 3j, that's a vector, but just look at the values. That definitely doesn't have unit length. And so lambda is defined as a unit vector. So it's got unit length. The way to make sure that this vector has a unit length is to what's called normalize it. So we're just going to divide by the magnitude of this vector. So that just means figuring out the magnitude and dividing through. So down in the denominator here, we basically have square root of 2 times 3 squared, or 3 root 2. And notice also for every lambda, we're going to have dimensions that cancel in the numerator and denominator. So again, lambda is a vector that has unit length and no units. It's a dimensionless unit vector. You can think of lambda as basically just your index finger pointing in the direction of that vector. Okay, so let's clean this up a little bit. The vector TBE, well, that's the unknown magnitude TBE, which we're trying to figure out. But remember that TBE is equal in magnitude to TBF, and so we're just going to call that T for the rest of the problem to keep things a little simple. So we'll make that substitution here. T times lambda BE. So lambda BE is -3 over 3 root 2 I plus 3 over 3 root 2 j. And then of course we can distribute this magnitude into this parenthetical here. So cleaning this up one more time, we'll just get that the vector TBE is -3t over 3 root 2 I plus 3t over 3 root 2 j. So this is the first of 3 tension vectors that we need to define here as well. Okay, so I know this process seems a little bit tedious, and I'm going through it a little bit slowly just to make sure I don't skip any steps in the explanation, but we do also need to define the vector TBF as well as the vector TCD before we can actually do the cross product to take moments about point A. To figure out TBF, we're going to just say that's the magnitude TBF times the unit vector lambda BF. Of course, the unit vector lambda BF is the vector from B to F divided by the magnitude of that vector. So if you go back up to our diagram, you'll find that the vector from B to F will take us in the negative x direction by 3 feet, as well as -6 feet in the z direction, noting the directions of the positive x and z axes here. So for the vector BF, again, -3i, -6k feet. Now that's the vector that goes from B to F. Of course, that does not have unit length, so again, we're going to normalize by dividing by the magnitude of that vector. In this case, that just happens to work out to 3 root 5. You also notice that the feet, the units cancel out, again leaving us with a dimensionless unit vector for lambda. Remember that the magnitude TBF, we're just calling that T because it has the same magnitude as tension TBE, and then we're just going to distribute that T into the lambda vector. So again, -3 over 3 root 5, that's -1 over root 5. I typically don't like to see square root in the denominator, so I'll multiply top and bottom by root 5. So that gives us minus root 5 over 5, t in the I direction. And then -6 over 3 root 5 by a similar approach gives us -2 root 5 over 5t in the k direction. Okay, so we went through that process a little bit quicker. We'll take the same approach for TCD. Now that's going to be equal to the magnitude TCD times lambda CD. Again, lambda CD is equal to the vector CD divided by the magnitude of that vector. So again, referring back to our diagram, pretend you're standing at point C. How do you get to point D? Well, you've got to backtrack along the x-axis by 7 feet, and then you're going to go in the positive z direction by 4 feet. So again, -7i plus 4k feet. And then of course we need to divide by the magnitude of that vector, which in this case is root 65. You know, the numbers aren't always going to be super nice. It is what it is. But again, our feet cancel, so we're just left with a dimensionless unit vector. Okay, so then cleaning this up a little bit, the vector TCD is equal to the magnitude TCD But recall that this tension is a totally different force. So whereas TBE and TBF were equal in magnitude, so we just called it T, TCD is a totally separate cable, so we have to treat that as a separate variable. Okay, so then we're going to distribute that TCD into the lambda vector, so we're going to get minus 7 over root 65 TCD in the I direction plus 4 over root 65 times TCD in the K direction. And I know I just said I don't like seeing square roots in the denominator, but I didn't want the numerator to get too funky looking either, so in this case I just left root 65 in the denominator. Okay, so that actually takes care of all of the vectors, TBE, TBF, and TCD. We've got RAB and RCD already, and the 300-pound force is a known vector in the negative J direction. So really all that's left to do is to now execute. We just have to do the math that is the sum of moments about point A, which basically just means taking 4 cross products. So starting with the first one, RAB cross TBE, we're going to take the determinant approach to compute these 4 cross products. Now what that consists of is constructing a 3x3 matrix where the top row are the 3 unit vectors corresponding to the 3 coordinate axes, and then the second row is RAB, and then the third row is TBE, the 2 vectors that you're trying to cross. So RAB is 3 feet in the I direction, and then 0 feet in the J and K direction. And then for TBE, we just have to refer to our derived vectors up above. There's an I and a J component, but no K component. And what this determinant represents is the cross product of RAB cross TBE. Okay, so that's the first of 4 cross products that we have to sum together. The next one is RAB cross TBF, which again we can express as the determinant of a 3x3 matrix. We've got IJK as the top row, RAB as the middle row again, which again is just 3, 0, 0. And then in the last row we've got TBF, which has an I component, no J component, but it does have a K component. Okay, so again the determinant of this 3x3 matrix represents the cross product RAB cross TBF. Okay, so a couple more that we just need to deal with. This one's going to represent RAC. RAC is a vector that has 7 feet in the I direction, but 0 feet in the J and K direction. And then we just need to cross that with TCD, which was this last vector that we just computed. It has an I component, no J component, but it does have a K component. And again, the determinant of this 3x3 matrix represents the cross product RAC cross TCD. And then of course there's one last one. It's RAC cross the applied 300-pound force in the negative J direction. This matrix is actually pretty sparse. It's just RAC is 7, 0, 0, and the applied force is 0, and then minus 300 pounds in the J direction, and then 0 in the K direction. So again, this determinant represents RAC cross the applied 300-pound force. And then all of this does need to sum to 0 because this entire summation represents the sum of moments about point A. Okay, so I know it's pretty involved at this point, but you got to remember what this all represents. So this entire thing here, that is the sum of moments about point A, and that entire summation needs to equal 0 because that's one of the equations of static equilibrium. So now really all that's left to do is to just do these 4 determinants and then see if we can equate some coefficients so that we can solve for the tensions. So fortunately all 4 of these matrices are pretty sparse. If you look at the first 3x3 matrix here, you'll notice that if we evaluate the I component, we're going to get 0 because the 2x2 determinant has a bunch of zeros in it. The J component is also going to be 0. The only term that survives from this determinant is the K component. So we're going to have a 3 root 2 over 2t in the K direction. So that's the only term that survives from this first determinant here. Pretty similar for the second determinant here as well. We've got the I component will annihilate. The K component will be 0 as well. And there's only one term that survives from the J component, and that's going to be a positive. It's going to be 6 root 5 over 5t, and that's going to be in the J direction. So that's the only term that survives from this second determinant here. For the third one here, okay, if we isolate I, that annihilates. If we isolate K, there's no K component either. So again, we have a situation where the only term that survives is from the J component, and so we're going to have a minus 28 TCD over root 65. And that's going to be in the j direction. And then lastly over here, this is a really sparse matrix. The only term that survives from this determinant is going to be from the k term, which is a negative 2100. And all of that has to equal 0. Okay, so fortunately the math actually reduced to something pretty straightforward. Now this is a vector equation, so some people will do this. They'll put a bar over the 0 on the right side. And what that means is that if the left-hand side is truly going to be equal to 0, then the j terms must add up to equal 0, and also the k terms must also add up to 0. So that's what I meant when I said that the sum of moments vector equation will actually give us 3 independent equations, because we're going to equate the coefficients for the 3 unit vectors. Okay, so generally speaking, you could get 3 equations out of this. If we look at the I components, well, we see that there are no I components in the left side of this equation. So we just get 0 equals 0, which doesn't give us any new information. But in some cases, when you equate the I coefficients, you will get some additional information. When we equate the k components, however, let's start with k down here, we see that, okay, 3 root 2 over 2 times t minus 2100, well, that has to be 0 because all the k components combined have to equal 0. And this will allow us to solve for t, the tension t. So that's going to be 990 pounds. This is equal in magnitude to both TBE and TBF because, again, it's the same cable. They're passing through a frictionless pulley. So that's one part of the solution. The second part of the solution comes from equating the j terms here, right? So the j components, we've got 6 root 5 over 5t minus 28 TCD over root 65. That's also got to be 0 for the entire left-hand side of this equation to be equal to 0. Well, we just figured out that t is equal to 990, and the only variable left to solve for is TCD, which we calculate as 765 pounds. Okay, so we've got our tension in cable BE, tension in cable BF, as well as tension in cable CD. Let's see if we actually answered the question here. Sometimes you kind of lose that in the mix here. The question was to find the tension in each cable. So we did solve the problem. We figured out TBE was equal to TBF, and we also calculated TCD. Now recall that we only used 3 of the 6 available equations of equilibrium in this problem. Again, we only used sum of moments about point A to solve the tensions in the cables. It's possible that the question would also have asked us to solve for the reactions at point A, which are another 3 unknown variables. And in order to figure out those components of the reaction, we would then have to invoke sum of forces x equals 0, sum of force y equals 0, and sum of force z equals 0. Those are the equations that would allow us to solve for the remaining unknowns. Okay, so this problem is getting pretty long already. We're going to stop there. We answered the question of solving for the tension in each one of the cables. I do realize that this was a pretty big problem, but what I tried to do was make sure that we started with the process. You know, of course, first step was to get our free body diagram. Second step was to develop our roadmap or our plan. In our case here, the overall plan was to take moments about point A, and that led to a symbolic expression comprised of 4 independent cross products. And once we had that, the rest of the problem was mostly just mathematical and less conceptual. In other words, once we set up our roadmap, once we had that equation down, the rest of the problem was basically just defining a bunch of vectors and then doing a bunch of cross products to solve. Okay, and to me, that's the best way to approach these vector statics problems, is to always start with the plan, essentially solve the problem symbolically, and then go back and fill in the numerical values. Okay, but again, if you have any questions on this problem, just feel free to drop them down below. We'll try and answer as many as we can. Definitely feel free to browse through our channel. Again, we've got hundreds of videos produced by our own faculty here at Cal Poly Pomona. This is a free resource for anybody out there, but these videos should be especially helpful for students at Cal Poly, because again, these are videos produced by faculty who teach the classes here at our university. But anyways, that's going to do it for this one. Thanks again for watching, and thanks for subscribing to our channel here in the Department of Mechanical Engineering at Cal Poly Pomona. We'll see you next time.